Welcome. Today is November 19th. I hope you guys received the message earlier because Canvas on Compare Zoom, it still shows that next week there are classes. But of course, there are no classes next week because of the holiday. And I had to send a message to everybody so that you guys are not expecting a class during Thanksgiving week, especially the one on Thanksgiving Day. And because again, when I make the announcements, when I make the Camp for Zoom from the beginning, it includes the entire semester. It doesn't know when we're taking breaks, so I sent a message earlier to that effect. Okay, so we have quite a few things to cover today, so I hope that we get through all of them. We're going to cover basically the fact that light is a quantized concept, basically, or light is quantized, basically. It comes in quanta, namely photons. And also we're going to talk about quantum mechanics and its principle. At some point, we're going to get into a beautiful, beautiful equation that that is not, in a sense, real. Equation is not real, but the results it yields are very much real. Okay. Unlike F equals to ma, this equation is a complex equation. Actually, it's called an imaginary. It has an imaginary number in it. Okay, so which means that you cannot really physically find a meaning for it. But the results it yields are actually one of the most accurate, if not the absolute accurate results that man basically has invented in terms of theory. Quantum mechanics, that is. It's far more accurate than classical mechanics of Newton. It's far more accurate than the theory of relativity of Einstein. It's far more accurate than anything else mankind have invented. But the theory itself, or the equation itself, as I said, is an imaginary equation. It does not exist in real life, and the function that it uses actually doesn't make sense in terms of, doesn't have a meaning really. But the results it yields are some of the most powerful results that can ever be. Oh man, what does this mean that the governor has announced? I just saw on my watch and actually on my phone that the governor has issued a month-long curfew. Cannot, because I'm planning to be tomorrow on campus. Hopefully they don't deny me access. Anyway, so let's get going. No, not that one. Let me find the file. It's this one. Okay, again, we have a couple of concepts that we're going to be covering in this chapter. And today, actually, I'm sorry, 2 chapters, actually 31 and 32. And namely the fact that light is quantized. And second one that we get into the atom, the model for the atom. And there are basically, we went through 3 stages. The first stage was that of Mr. Niels Bohr. And then Mr. Louis de Broglie. How do you say? Louis de Broglie, I don't know how. In French, it's Louis de Broglie, that says French. He's the one who came up with the correction to Niels Bohr's model. And because Niels Bohr's model leads to an unstable atom. And then, of course, we came up with a far more better approach to it, namely using quantum mechanics, which is really more accurate than anything else for the atom. So this is basically the whole idea in here for these 2 chapters. So, again, the birth of quantum theory, and it started with Mr. Planck, a German physicist, studying the black body radiation, and for that to make sense to him, or at least for the black body radiation to make sense, and with the experiment, light has to be quantized, has to be in little chunks, bits of light, basically. Light is not like we thought before, it was a wave, okay? And those chunks, later on, they were named photons. They are particles of light, really. That's what a photon means. And now we have the first really attempt to it. And there is a correspondence one-to-one between the energy of light and the frequency. Okay, the constant between them is actually what is now known as Planck's constant, which is a constant we saw the other day, 6.6 times 10 to the negative 34, okay, in our size. Tiny, tiny number, okay? We're going to discover the photoelectric effect. Basically what it is you take a metal, you shine on it light, depending on the frequency of the light, not the intensity, the frequency. You could release electrons from the metal. Okay, so light hits light, which is made up of these tiny particles. When they collide with the electrons, they eject the electrons from the metal. That electron, the speed with which it merges depends only on the frequency. It doesn't depend on the intensity of it. Okay, the intensity, you're going to get more electrons ejected, but not faster. So that was the photoelectric effect, and that puzzled scientists for a long time, at least for a short period of time, and during that time, until Mr. Einstein came up with a beautiful explanation for it. And that's how Einstein actually was famous. He was famous for the photoelectric effect. Later on, the theories that he discovered for relativity and all of that became important, and he became famous for them. But the reason why he won Nobel Prize is because of the photoelectric effect. Okay. Then we're going to discuss the wave duality. Is light a wave? Is light a particle? It's both. Okay. We did the double slit experiment when we were talking about the fact that light is a wave, that Mr. Young in the early 1800s, when he discovered that light is a wave. And we're going to talk about that now in terms of electrons. Electrons are particles, but sometimes actually they behave like waves. So the electrons also have this duality. So it's not just light itself has this dual personality, wave and particle. Electrons and particles actually in general do have that effect. So electrons do diffraction, they do interference, they do all of the fringes, the bright and all of them. Okay. And then we'll get into the uncertainty principle. The uncertainty principle is really at the heart of modern physics, or at least quantum mechanics, that is. We cannot talk about the position of the electron, because if I determine its position with an absolute accuracy, I have no idea how much its momentum is. Okay, if I know its momentum with the absolute accuracy, the electron could be anywhere in the universe, not just in the atom. Okay, so that's in a nutshell what the uncertainty principle is. Okay, and that leads to another difficulty in that the experiment itself affects the state of what you're measuring. Okay, so it goes back to the idea: if a tree falls from in a forest, would it make sound? Does it make sound because we hear it, or does it make a sound inherently? That is the fact that you go and hear it. In this case, actually, the person is there to observe it, is the reason why it makes sound. So I know it doesn't make sense to you, this term, but that's exactly what's going on sometimes in terms of the quantum level behavior. There is another uncertainty also principle in terms of the energy and the time. That too has the same correspondence as the momentum and the velocity, and the momentum position, I'm sorry. Okay. And then there is the idea of the complementarity, which is really something that we're going to get to it at the end. We're going to go to the next section, which deals with the discovery of the atomic model, and that's actually Mr. Niels Bohr is the one who first theorized that the nucleus, based on the observation of Mr. What's his name? Rutherford. He did experiments basically by having gold foils, and he shone on them alpha particles that are emitted by certain radioactive materials. As they go through them, most of the alpha particles go unimpeded through, meaning that the gold foil itself, whatever it makes it, is mainly empty. There is nothing in it, because most of the particles, they go through the gold foil as if there is nothing inside there to prevent them from going through. Some of them, though, are deviated, okay? And some of them actually bounce back, okay? Indicating, because the alpha particles have positive charges, that the nucleus of the atom, of those gold atoms, must be positive charged, and it's tiny, very, very small, tiny thing. So those are the experiments that led to that. Of course, we were able to find the mass of the electron. We were trying to find with the experiments of Millikan, and also the charge of the electron. So that's really a lot of things that we were able to determine at that point. Mr. Niels Bohr put them together, and he came up with a model as follows. The nucleus is like the sun, and the the electrons are like the planets, basically, in a planetary motion. And he was able to explain one of the things that was discovered earlier, that is the energy levels in terms of the hydrogen, for example, spectrum. That was beautiful. But immediately he was hit with a huge criticism in the fact that this model is not stable. Because if the electrons are moving around the nucleus, they must be accelerating with acceleration, which is v squared over r. That is something that we know from classical mechanics. An object that goes in a circular path, when you turn, for example, your car, you find yourself basically pushed to the other side because of the inertia. There is an acceleration which depends on the radius of curvature. Okay, that is exactly what's going on in here. If you're going straight and you have your cruise control, you don't feel any acceleration. But if you go one side or the other, if you have something hanging in your rear view mirror, it's going to deviate one way or the other depending on which way you're turning. So there is an acceleration, and the only reason why it goes back and forth is because of the inertia. So there is an acceleration for these electrons. Classical mechanics, especially a theory of Mr. Maxwell, state the following. The result that it comes in. If a charged particle is accelerating, it is going. What is this bug in here? Sorry, I have a bug in here. Oh man, what is this? It's a flying bug. Anyway, let me get rid of it, okay? Anyway, sorry about the disruption. Anyway, so what this means is that these electrons, as they're going around, they must radiate energy. Because an accelerating charge will radiate energy, just like the antenna, okay, in the dipole. So you have a problem now. So these electrons cannot stay stable. They have to collapse immediately on the nucleus. So Mr. Louis de Broglie came up with a model that fixes that problem. And he basically assumed that in this case, for the electron to stay in orbit, it must have a standing wave. In other words, its wavelength must be multiples of the radius of where it is sitting. And now all of a sudden, the theory is fixed again. But there are some troubles with it. It's not just this one, until the advent of quantum mechanics that fixes everything. Again, when I discovered how the electron was discovered, it was discovered with J.J. Thomson's experiment first, basically that the particles, as they are emerging from basically charged plates, they deviate under a magnetic field indicating that they have a charge. Not only that, Mr. Millikan was able to find what that charge is and what that mass is, and that's how the electron actually was found in terms of its properties, okay? And then we're going to talk again, I talked about the Niels Bohr's model, okay, and how the energy levels can be explained, and improvements on that, and then quantum mechanics, namely first of all, the principle of uncertainty of Mr. Heisenberg, and then also the Schrodinger's equation actually is the one that fixes everything. Okay, Schrodinger's equation is the one that I was talking about, the fact that it is an imaginary equation with a mathematical function that has no meaning in real life, yet the results that it yields are the most accurate results that man has ever invented. This Schrodinger's equation, which we're going to get to it at the end, basically is the equivalent of F equals to ma. That is in classical mechanics. So it's a principle. Combined with the principle of uncertainty, basically do everything that you need to do in quantum mechanics. The correspondence principle is the one established later on to basically state the fact that the theory cannot discredit any work that was done before it. It must build on the old stuff. Since when we go through the Niels Bohr's model, that Experimental experiment, then came Louis de Broglie that fixed some problems with it and retained the old results until quantum mechanics did both and actually improved on both of them. So this is actually an approach that you have to have in mind when you're building theories, really. So this is in a nutshell both content. No questions? If you're wondering about the bug, it's dead, okay? Sorry if you're sensitive to that. Okay. Okay. Okay, so there has been a long historical debate about the nature of, again, light, whether or not it behaves like a particle and a wave. And I think we talked last time when we saw how the idea evolved over centuries. Actually, we went from complete particle approach to wave approach, and the only way to do business is wave, to formal powerful theory by Mr. Maxwell that it is actually a wave, and here its wavelength and its frequency and everything else. And then came this experiments of the photoelectric effect that ruined the whole picture that we built so far. And light, all of a sudden, again, it became particle again, and we actually gave a name for these particles in here, which were called photons. Also, Max Planck's experiments on the black body radiation reiterated what we already have in terms of what we suspected now, that light is a particle. So, and then what is it? And the answer to that in a nutshell is both. Okay. Because technically these are two excluding ideas. A particle cannot be a wave, and a wave cannot be a particle. So technically you cannot have your cake and eat it too. What is that thing there? You cannot, these are antagonist ideas completely against one another, but light does both. Okay. Once you get into the realm of quantum mechanics, a lot of the things that make sense to us on a daily level, they become basically kind of weird on that level. Okay, at least the things that are on the quantum mechanical level, they are weird on our level in here. And it has to do with that constant. Remember that constant that we talked about last time, where 6.6 times 10 to the negative 34. This is Planck's constant. If this was not so tiny, this is 0.34 zeros before you reach the first digit. Okay, so this is a very, 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 very small number. If this was not 10 to the negative 34, but like, for example, 10 to the negative 1, we would be living in a quantum world. Everything will make sense to us. It will be weird, for example, if we don't see a wave and a particle in the same sense together. A person could be at home sleeping and in the same time in the office working, if this number was any bigger, because you could be in two places at the same time. And then there is no need for walls, because you could basically tunnel yourself through any wall. You can get through it any time. So if you want money, you can just basically grab it from the bank. You don't even have to ask anybody. You just put your hands in and go through it. So again, a lot of these things, they seem weird and inconceivable, because this constant, Planck's constant, happened to be so tiny that it works only on this level. It doesn't work on our big scale. Okay. Again, this is the idea behind it, that now light is quantized because its energy is actually quantized, and its energy comes in chunks. Okay, and it's proportional to the frequency. Okay. So the idea that nature world is granular rather than smoothly, that's what the quantization means. And quantum, any elementary particle that makes up both matter and carries energy. Okay, so that's what quantum is. So a photon is a quantum, basically, particle. Electron is a quantum particle. It turns out the proton actually is made up of other things. Okay. Again, I mentioned the photoelectric effect, the fact that the energy is proportional to the frequency. Here is a photoelectric effect. In this model, this is the experiment if we were to do it in the lab. I don't think that this experiment for physics 11, but this is the experiment if we do it in the lab. Forget about the battery for right now. Okay, let's ignore the battery. But if you connect a wire in here, just like this, and another wire, so this would not be charged now if there is no wire, no battery. And if you shine light on it, what happens? If the light has this right frequency, not intensity, not as bright as it can be, no, the right frequency means that the laser has to be tuned into the perfect frequency. Then in this case, this metal will eject electrons, and that could be captured in here, and then Now you have, since an electron is lost from here, so I'm saying from this side, so this will be positively charged actually, and this will be negatively charged, so the electron will continue in its path to close the circuit. You will see current. In the lab, the way we do it actually is we take this plate, and then there is another plate. Again, we shine light on it, okay, expose it to light. And we have, again, the ammeter in here. We want the ammeter to read 0, so we apply the voltage actually in the opposite direction, okay? We apply the voltage, in this case, in the opposite direction. What am I doing in here? Okay. To force. So as the electrons are moving this way, I want to change the voltage in here to just balance this electron so that the current will be 0, if we did this experiment. I know how much voltage I have applied in here. Usually this is not how it works, because you have actually a rheostat in there to control the resistance and to control the currents and the voltage in this area. Once you know exactly what the voltage in this area is, then you know how much voltage actually was needed to grab these electrons and move them this way, so that the current actually stays 0 in here. If you see current going this way, that means that you're pushing too much current this way, so you need to reduce it. If you see the current is going this way, that means you're not pushing enough current in this direction. Okay, you need to increase it to compensate for a lot of the charges that are moving one way or the other. Again, this is the photoelectric. The only reason why the charges move and are liberated actually from the metal is because they are hit with the right photon that has the right momentum. This is a collision, classical collision between two particles. So this is a particle behavior. Light is a wave. If a wave hits a particle, there is no way for it to collide. There is no collision between a particle and a wave. The only way to explain this phenomenon if you have two particles hitting one another, no wave involved. So the assumption in here that light must be a particle to do that. But it has to have the right momentum to eject those electrons, to give them enough, basically, kinetic energy so that they free up. Because every metal, you cannot remove its electrons easily, depending on basically what is called the work function, depending on its properties and its chemical properties, basically, how bound the electrons are to the metal. But if you have the right energy for them, they will be freed up. So that's why actually you will see that this voltage, there is a threshold for it before you actually get into the actual electron starts to move. You will not see current moving unless you have the right frequency. So as you change the frequency higher and higher and higher until you get the right frequency, then a bunch of electrons start to flow, depending on how much light you have, how bright the light is. The brightness of a light determines basically how many electrons will eject, that's all. Does not determine if the electron ever is ejected or not. What determines that is actually the frequency. So again, here is the point. So this happens whether or not you have a voltage or not. So this experiment in here is irrelevant whether you have a battery or not. Okay. So the fact that you have a metal in here, depending on its work function, the frequency in here from the light need to be the right one for you to eject an electron to begin with. If you bring two light bulbs in here, they're going to emerge with the same kinetic energy. They're going to emerge with the same velocity all of the electrons do, but you'll have more of them. That's all. So instead of 3 of them, you will have 6 because you doubled the intensity. That's all. But you're not going to get them faster. You're going to get more of them. So low frequency will not do anything. High frequency will get you the electrons to move. So that was the photoelectric effect. Again, the only explanation is that these photons, the particles of light, now have high enough momentum and high enough energy to cause this thing to happen. Because the assumption is the energy is proportional to the frequency. So if the frequency is high enough, that would be high enough energy to collide with the electrons in here and give them enough momentum, enough energy to escape what is holding them in the metal to begin with. Okay? So it was Mr. Einstein actually who explained this phenomenon beautifully with his work, and that's how he became basically a household name in the beginning. That's how he won the Nobel Prize actually. So in the photoelectric effect, the brighter the illumination light on a photosensitive surface, the greater the not the velocity, because the brightness is the intensity, how many photons come in. So this will correspond to how many electrons are ejected, not how much energy they will end up with, okay? That is determined only by the frequency. So the correct answer is B. This is question of the day today. That the intensity of the intensity of light will affect the number of ejected electrons, not their speed. Does this make sense to you guys? The intensity of light in a photoelectric effect impacts how many electrons are ejected, not their energies. Got it, everybody? At least those who are here. Any confirmations? Okay, at least one person. Josh also. Good. So that is basically item number 1 today. And the second question is just completion of the first, what we just said, okay? So a photon behaves as a particle when emitted by an atom or absorbed by a photoelectric effect, but it behaves as a wave when it's traveling. Actually, it does it all the time, okay? It does both of them, okay? In this sense, light can. So here is basically, as the intensity grows of the photons, they build more and more the picture in this case to give you a more accurate picture. So these are electrons actually, okay? I'm sorry, photons, what am I saying in here? So they give you a better picture in here when they impact a film in here they develop, okay? This is the double slit experiment that some of you guys who are physics 11, I'm sorry, you're doing right now. So light being a wave in here, I have a monochromatic beam. I have the same frequency. That's what monochromatic means. It goes through a double slit, meaning there are 2 openings in here. Usually the openings are comparable to the wavelength, okay? They cannot be too wide. They are too wide, then you're not going to see, you're going to see a big, basically, light in here. Then what you will see in the here is going to see a repetition of these fringes, dark fringes, bright fringes, dark fringes, bright fringes. And this can only happen if there is constructive interference in the bright fringes. So this is constructive. And there is destructive in these regions when the waves, they come out of phase and they cancel. Particles do not do that. This particle, for example, let me get another object. I don't want to pick up that one. Yeah, this magnet. No, I have this one. Actually, that's what I did. Those particles cannot have this wave. You still have them, both of them distinguishable from one another. This one, this, the other one is that. No matter which way you put them, and if I tell you to close your eyes, can you find them? You always are going to find them. But with the wave, during the interference place, you're not, they lose identity and they become something new, okay? They combine in here, so you cannot tell where the first one is and where the second one is. And in here, actually, they cancel completely. They are completely disappearing. So that's because light is a wave, okay? Which begs the question, what happened in here in this case for the photons when they're going through the slit? Each slit, they are going to have their waves, and when they combine now, if you increase their intensity, they are going to make this again, this fringes again, bright and dark fringes. If only one of the slits is actually open, the other one is closed, as long as they are not too small, because if they are too small, actually there is another kind of interference that's going to appear because of the diffraction. But then in this case, you'll have a big blob of light by itself, only one spot, no more. So if you hide the first one, the top one, you're going to see a big blob by itself, by a bright spot by itself in here. If you hide the bottom one, you're going to see a big bright spot on the top. That's it. But if you have them both open, now bright, bright, dark, bright, dark, so many of them, okay? How did they come up with? It's because of the interference. So light is a wave, okay? So again, this nature in here between wave and particle is what light does all the time. So depending on the phenomenon. Mr. Louis de Broglie, I think that's how they say it even in English. It would be weird to say it Broglie. Okay, Louis de Broglie is the one who basically postulated the momentum. And for the light, and light actually has a momentum too. And so now momentum means actually a particle. Because momentum, when we took mechanics, we said it's mass times velocity. So momentum in here implies particle behavior, okay? And he was able to actually, based on this formula, to find what the momentum is based on the wavelength, okay? So if we do that, then things start to make sense again. Now light is a wave, and in the same time is a particle. When we speak of de Broglie's waves, we are speaking of the wave nature of particles, basically. Okay, which is kind of it sounds like it's contradictory statements, but that's exactly what it is. Again, for the electrons, they also behave in similar fashion because of the fact that also they actually can behave like a wave, and they can actually produce images, like for example in an electron microscope. I mentioned the uncertainty principle, and the uncertainty principle is really one of the principles. Again, principles is not something to prove, it's the results that prove it, basically, in a sense, okay? So, and in this case, it's one of the foundation of newer mechanics. That, for example, this expression, what it says is the following. If you know with absolute accuracy the momentum of a quantum object, like for example an electron, you cannot know where it is. Delta X means it's where is it in space? It's completely unknown. In other words, how certain are you the electron is here or there? Absolutely no idea, with an error of 100%. Okay. H bar is that number that showed you earlier divided by 2 pi. So it's really 1 times 10 to the negative 34. Okay. H bar is just the same H that we saw earlier divided by 2 pi. Okay, which is just a constant. Sometimes it comes in this combination. So instead of using H divided by 2 pi, people gave it the name H bar. Okay. So what this expression says again is that if you know exactly where the electron, if you were able to pinpoint where it is in space, then you have no idea how much momentum is, because the error now is 100%. So this momentum can be anything, okay? We have no clue about it. So if I want to do any significant measurements, I really have to take this principle into account, okay? This, combined with the equation that comes toward the end of the discussion, are actually the foundation of modern quantum mechanics. Not that there was a classical quantum mechanics, at least quantum mechanics in general, which is one of the modern physics there is. So again, this is just an explanation of what I was talking about. Same thing happens actually with this expression too, between the energy and the time. So again, if you know how much precisely an electron has in terms of how many joules it has, or electron volts, that's another way of measuring energy, you have no idea when that happened. The past and the future, as a matter of fact, you have no clue. The error on the time is infinite. It's actually 100% in this case. If you know exactly what time the object is, basically in a special state, then you have no idea how much energy it has. Again, this is the principle of uncertainty. This is due to Mr. Heisenberg, okay? Not the one famous from that, what is that chemistry thing that who was making drugs in New Mexico? There is a movie along this lines, or show or something like that. Anybody saw that thing? Yes, Breaking Bad. Yeah, not that Heisenberg. This is the real Heisenberg, okay? I think the name Heisenberg was inspired from this guy, okay? Or at least he borrowed this guy's name, okay? So again, Heisenberg uncertainty principle applies only to quantum mechanics. It does not apply to uncertainty of a macroscopic laboratory, because in a macroscopic laboratory, this number really is 0. For a macroscopic object like you and I, this number is 10 to the negative 34, basically 0.000000000000000 34 before you get into 1. Okay, so for us, for our measurements, 1 meter, 5 centimeters, 10 centimeters, this number is so tiny that this principle does not apply to us. Okay, so that's basically why we're saying that. But for an electron, this number becomes important, becomes significant. So if you're describing the state of an electron, then it becomes very, very important. Okay. The idea that wave and particle is what we mean in this case, complementarity, and also the time and energy versus the position, and also momentum. But it's just a way of accepting these things from now on, just like the yin-yang. Okay, which brings us to the second topic of the day, the atom and the quantum mechanics. Again, I mentioned Mr. Rutherford experiments using gold foil, okay? And the alpha particles are basically the ionized helium. Okay, it has 4 nucleons, basically 2 protons and 2 electrons. Okay, that's what it is. And it has no charge, of course, so it's positively charged. So that's what an alpha particle is. So if you hear me say the alpha particle, that's exactly what it is. For those of you sitting in physics 11, we're going to have a big lab on the alpha particles and beta particles, and actually alpha and also gamma rays. So that's really something. For those who are not sitting in physics 11, you're fine. Okay. So again, the alpha particles, as they emerge in here, they're collimated, meaning that they're going through a beam. Okay. So as they go through the foil in here, for the most part, they go unimpeded. Meaning that the atoms they go through are completely empty space for the most part. So the atom, actually the distance between the nucleus and the electrons, this distance is about 10,000 times than the size, for example, of the nucleus or the size of the electron. Okay, so this is a huge distance. Okay. For the most part in here, the alpha particles, they go straight out. They completely have no. Some of them that hit the nucleus, they bounce back. Some of them actually they come too close, where because alpha particles have positive charge and the nucleus is positive charge, they're deviated. So those are the ones we see here. And the deviation in here depends on the angle of incidence. If this is the nucleus, and if you are coming head on, then you're going to bounce back off. If you're coming too close, then you're going to bounce off this way. But if you're coming very far away, maybe you'll be impacted this way. So again, depending on the angle in here with which they're going to come, that's basically how we determine the reflection. But for the most part, the alpha particles, they come straight through completely unimpeded. They are too far to be impacted by the nucleus. That means that the nucleus is so tiny inside the atom, so small compared to the atom itself. That's why, for the most part, the alpha particles are completely unaffected by the nucleus, and they are positively charged. Okay, so some of them, very few, they probably will return in sharp angles, but the vast majority, if any deviation, is going to be small, but the vast majority, they're going to go completely unaware of the fact that there is a positive charge in here. So this is how we got an idea into how the atom is basically made up of. So the nucleus is very small, okay, and it's super dense in terms of mass. It's where most of the mass of the atom is, okay, because it turns out, based on the measurements that we did using Rutherford experiments, is that the mass of this guys, because you know the mass of the alpha particles basically, so then you can deduce the mass of the nucleus based on that, and the mass of the nucleus is mainly the mass of everything in here. It turns out it's almost 2,000. One proton, it's 1,900 and something, 1,980 to be closer. The mass of the electron. So this is the mass of the proton or the mass of the neutron. They're roughly the same number. Okay, they're much bigger than the electron. So most of the mass of the atom is just sitting in its nucleus. Okay, so we have this model right now. Now the electron itself, we were able to measure its beam. So if you have, for example, a battery in here of high voltage, and you have the cathode now connected to the negative side of the battery, the anode in here, and you have a gas in here, and you increase the voltage, of course, there are charges that start to fly, in this case, electrons. If you put a magnet in here, that magnet will show that this particle starts to deviate, deflect. And that deflection gives me the sign for them, and they are negatively charged, first of all. And I can experiment with this one based on the intensity of the magnetic field in here. Based on the intensity of the electric field in here, I should be able to find the ratio again of E over M. Okay, the ratio of the electrons charge versus the mass of the charge. If I can somehow find the electron charge, then I can find what their mass is. As a matter of fact, the next experiment by Mr. Millikan is the one that determined the charge. Because Mr. Millikan, what he did, he took a suspended oil in here in this chamber, and they are actually charged suspensions. It's charged basically a particle, and he put them inside the plates also. And he changed the voltage in such a way that the charges will be suspended. He looked at them in a microscope, and he saw the oil, basically droplets, suspended. From there, he was able to find the necessary charge, at least that needs to balance both. At that point, when they're suspended, it needs only to balance the gravity, because they are not moving. Initially, when they are moving down, there is a viscosity which is going to slow them down. But once they reach basically once they stop, at that point there is no viscosity you're going to worry about. You're going to worry about the gravity, which is mg, and this in this case is just their charge q times the electric field that is established in here. Based on that, again, we can find what q over m is. What he found actually, that all of these q's in here are multiples of a simple number, all of them. He did this observation over a long time. So Mr. Millikan was convinced that this is the charge of this electrons. So the charge must be 1.610 to the negative 19. Since I know what the ratio of E over M is, then I know what their mass is. And from there, we determine what this particles is. Go back to Rutherford experiment. Now you can find what the nucleus size is. So it's backward in here. So now we know basically what these protons have mass and what they have charge, and neutrons, the fact that they don't have any. So that's, we learned a lot from this experiment. Okay. Again, also when we were doing when we excite an atom, it has this specific, and we talked about that last time, specific spectral lines, meaning that it has emission spectrum that follows specific lines in here. So again, in order to understand that, Mr. What's his name? Balmer is the one who found that there is a pattern here. First of all, there is a mathematical expression expressing the gap, the difference between this, for example, frequency and this frequency and that frequency in terms of the energy. And there is 1 over n squared that connects them. Of course, he didn't know what that was initially until Mr. Rydberg and other people came up with an explanation for it, especially Mr. Bohr in here, who postulated this theorem, his work in here, and basically the model where this, the nucleus is the center. And now we found this discrete energy levels that explain, among other things, Balmer's basically observation in terms of the spectral lines. Now the spectrum is beautifully understood, at least for the emission spectrum and the absorption spectrum. Okay. But of course, this model was immediately hit with a big criticism that these electrons, if they are exactly what you're saying they are, and they are charged and they're moving around the nucleus, they must lose energy due to the fact that they're radiating it. And then the atom is not stable. So I got, again, to fix that, Mr. Louis de Broglie basically came up with his model that this is actually waves, these electrons are. And they have, if they are in a standing wave, if they form a standing wave, if they have like a resonance in this case, they can stay in orbit, okay? And this fix the problem, and actually was able to go beyond and explain what this orbital motion is. So yes, if the wave does not close on itself, in this case, the electron cannot stay in that energy. This is not a stable configuration. If it closes on itself, then you have a stable configuration. How many times, how many modes you have, that determines actually the number in this case, and here the energy level that corresponds to that, where it can be exactly in such a way that the wavelength closes in itself depending on how far it is from the nucleus. So that's a model again. A model is not reality, by the way. A model is just an explanation of what we see, and then based on that, we go and observe things and it fits it. So it's not really, if you go and look, for example, an electron with your eye, and if you are able to get into that level and see it, it doesn't look like this model. This is just a representation of it, so that you guys understand. It's just a model. But then it explains a lot of the experiments that we were able to do, okay? So it must be correct to that extent, at least to that point, as far as the experiment is concerned. So again, this model explains why don't spiral closer and closer to the atom, because that's the closest that they can go in order to stay basically into a standing wave, okay? Then Mr. Schrödinger actually postulated this expression. This is Schrödinger's expression, okay? I know the details of the expression way beyond this course, actually. They are outside of the scope of this course completely. But let me give you an idea of what that says roughly, okay? This is a mathematical symbol. It's a very complicated mathematical symbol. At least even in the simplest form, it's very hard to write, okay? When it's normal operation, when you take it, for example, in the case of the atom, it's even harder to write because of the so-called non-Cartesian coordinate system that you have to deal with. This h bar is the same h bar we introduced earlier. It's the same h divided by 2 pi, which is roughly 10 to the negative 34. Okay? M is the mass of whatever you're going to study. So those have meaning. M has a meaning now. M is the mass of the electron, or mass of whatever you're trying to find in here, okay? U is the potential energy. Again, this is something that we discussed before. So this is the potential energy. We don't have a problem with it. I'm going to skip psi for right now. H bar is the same H bar that we talked about. And this curly thing in here, because this psi is a function that depends both on space and time, you have to tell it where are you doing your, where are you taking its derivatives? You're taking it with respect to time. So this is a so-called partial. It's not really hard to envision. When you have something in real life that doesn't depend only on one parameter, it depends most of the time on multiple parameters. So again, this is the stuff that, this is ordinary things to some extent. This is not too far. I mean, it's very, very complicated to F equals to ma, but it's to some extent can be approached. This is U where the energy is. So there is a room for maneuvering in there, okay, where each bar is just a constant. Here is the trouble. This guy and this one, the I is just the square root of -1, which is imaginary number. Did anyone hear about the imaginary numbers? Did you guys have them in your math class or somewhere or in high school or something? Heard about the imaginary numbers? Okay, very good. That means these numbers. Yeah, I met a lady actually, and she was in actually worked with her. She was actually a lab assistant, and she was saying that the thing that she learned in high school and she had no idea because it doesn't apply in real life are the imaginary numbers. Okay, well, here it is. Without imaginary numbers, you cannot do quantum mechanics. That's as simple as that. They are not real. They are numbers that don't exist in real life at all. The purpose of them is you take something that is super hard, like quantum mechanics, And you introduce imaginary numbers basically to make what is called the complex numbers. Complex numbers are a combination of what we know as real numbers and imaginary numbers. So you introduce these complex numbers that at least one of you guys hates them, and make life very easy for yourself. That's the trick with them. Okay, make the hard problem easier. But the trick with it, as you guys have duly noted, they are not real. They don't exist in real life. So this whole equation then is not real, meaning this psi also is not real. There is no meaning for it, not real. There is no meaning for this psi by itself, okay? Yet the beauty of this equation is the foundation of the most accurate theory in science, okay? Isn't this amazing? Isn't this one of them? Okay, no, forget about complex numbers or imaginary numbers. The equation itself, the beauty of the equation. I know some people who have it tattooed on their shoulders and backs and everywhere because how powerful, at least physicists are. I know probably some of you guys are not. They don't really think of it much, or at least they don't probably think that it is that not that much of a big deal, but it is. Okay, it is the most accurate thing that you can ever meet in your life, and at least it led to the most accurate science, which is the so-called standard model, which is really based on this thing. Okay, and it is amazing. Okay, and the thing with it is, it's not, you cannot explain it in terms of like F equals to ma, force, mass, acceleration. So that becomes a walk in the park compared to this expression in terms of explaining it, at least. But this one, the I itself makes the whole thing basically complex numbers. But psi itself does not have a meaning, but psi squared has. Psi squared has to do with the probability. To be more specific, the complex conjugate for psi times psi itself has a meaning, big time. Okay? That is actually where the whole heart of it is. Psi itself does not mean much, but its product with itself makes a lot of sense. It's everything in there, in that thing. Okay. So how far are we going to? Okay, we still have time. Okay. So in Schrodinger's equation, wave equation, the thing that waves is the non-material matter wave amplitude. So the thing that waves in this case, I know we did the lab on waves for physics 11, and we talked about waves, waves, waves. And when we hit this one, and we said that this is actually nothing waves in this case, okay? This is called the Schrodinger wave equation, but there is no wave. There is nothing that is actually really waves, okay? But there is a mathematical wave in this case, okay? And this function is called the wave function. And the name for it, the letter usually they use for it is the Greek letter psi. But everything, all the physics is actually contained in it. So again, here is the model is basically where we stand right now. We went from Niels Bohr's model to Louis de Broglie basically correction to Schrodinger's model that gives you all of this so-called S, P, D, F, and beautiful, beautiful theory, at least for the atom itself and far beyond, okay? So this is the second discussion of the day, is the evolution of this quantum mechanical models for the atom, okay? So we went from Niels Bohr model, where we basically have the nucleus is like the sun, and all the electrons like the planet, revolving around it. Louis de Broglie basically came up with the standing waves, just like when we do the standing waves on a string, okay, or the harmonics on a harmonica or any basically musical device, okay. So that is Louis de Broglie correction, and then Mr. Schrodinger came up with an equation that basically fixed the model once and for all. You guys understand the second task is to basically talk about the evolution of the atomic model, how the atom went from one model to the next to the next. Yes? Okay, at least one person. Anyone else? Should I repeat this thing? Okay, Kyle is good. Very good. So unless you guys want me to go through it again, we can but it's in this slide in here actually. What is this number slide in here? 52. Again, I mentioned the fact the correspondence principle is that the new theory must not invalidate everything the old theory did, because it has to build on it. Okay, so this is in a nutshell basically the content for these two chapters. You have a new assignment that I posted actually for you guys also, that is due actually the week after Thanksgiving. There is an assignment that is due, two assignments actually that are due after the week of Thanksgiving. And I want you to also pay attention, because we are really preparing for the final exam, which is going to be on December 10th. So the last time we will meet is going to be December 8th, but we have two classes before that on the first week of December. So I want you to really start thinking in terms of the final exam and getting yourself ready for it, okay? And please enjoy your holiday and stay safe. Do not, I think there was just a warning in here, or at least an announcement from the governor, that we cannot go out for a month and all of that thing. So please don't observe all the safety guidelines and everything else. And I'm hoping that my visit tomorrow to campus will not be canceled, because I'm hoping to see this new apparatus that we received from the US Navy for catapult, basically. What do you call it? Yeah, catapult. It's a big catapult. Well, it uses the word trebuchet. Okay, it's a big trebuchet. So I want to see if I can find basically some information about its range, so that we test it for my physics classes, the mechanical classes. So we'll see. Okay, maybe we can do a project for. I know it's too late for you guys, at least physics 11 guys, but maybe next semester for physics 11 we'll do some competition building our own trebuchets and see if we can who gets the furthest in terms of range and who gets also hits the targets. Okay, stay safe. For those in physics 11, I'll see you guys in an hour. For the others, I'll see you after the break. I'm gonna stop the recording first.